Proof using recurrence relation. Sum of Stirling number of first kind. Okay, we have already made quite a few videos on Stirling number of second kind, so I thought now it's finally time to move into the first kind, right? It's not really as similar as you might expect. But yeah, it's also about counting some number of ways of permutation, something like that. We'll talk about that, and then based on the definition of the Stirling number of first kind, would also derive a recurrence relation. I mean, that's just like combinatorial derivation using intuition, and then use that recurrence relation of the Stirling number of first kind will prove this formula. Once you have recurrence, it's not a big deal, but yeah, it might take some time to understand what this thing is, and then to find that formula. Okay, let me go with the definition of the Stirling number of first kind, right? Stirling number of first kind is defined like this. The number of permutations, or as I would like to say, permutation functions, like I will tell why later on, of an labeled elements. That means like distinct elements, let's say 1, 2, 3, something like that. I mean, it should be distinct, right? This should not be like really same thing. That consists of exactly k distinct cycles. Okay, now what do this cycle mean? Permutation function mean? We also have to go over that. It won't take a long time, but yeah, let me go over that quickly. So basically, let's say okay, what's permutation function? So let's say I have this arrangement of four distinct numbers, right? And like let's say p1 be a permutation that takes these numbers to, let's say, 2 1. Okay, let me say 2 3 1 4, right? Something like this. Or let me add one more number, 5. Then 2 3 1. Let's make it 5 for now. So okay, the arrangement of the first set of numbers has been changed over here, right? So this p1 is a permutation function that changes 1 2 3 4 5 arrangement to 2 3 1 by 4. So that's what permutation function is. And there's also this cycle notation to write permutation function. Okay. So let me first write the permutation in like top bottom arrangement 2 3 1 5 4. Now to write this same permutation function in cycle notation, what I can do is, okay, notice that over here this permutation takes 1 to 2, right? The first element becomes 2 now, and 2 to 3, right? And 3 just goes to 1, right? So this is closed, like 1 goes to 2, 2 goes to 3, and then 3 goes like back to 1. So this is one cycle. And now 4 goes to 5, and 5 goes to another cycle. So this is a permutation function with 2 cycles, okay? With 2 cycles. And then both cycles are disjoint because there aren't really any common elements in both, right? It won't really be a case in like the way I'm doing it. So yeah, it's a it's a permutation function with like n equals to 5 and with cycles k equals to 2, right? 5 elements, 2 cycles, and then yeah, 2 distant cycles, and yeah, this is how permutation functions are. Let me show you next one. Let's say p2. Take 1 2 3 4 5 to, let's say, 3 5 4 2 1, something like this, right? Now for this one I can write p2 as, okay, 1 goes to, okay, so over here 1 goes to, let me first write it in different notation. Okay, 1 2 3 4 5 goes to 3 5 4 2 1, right? So in cycle notation, 1 first goes to 3, 3 goes to 4, 4 goes to 2, 2 goes to 5, 5 goes to 1. So this is just one cycle. 1 went to 3, right? 1 went to 3, 3 went to 4, right? And then 4 went to 2, right? And then 2 went to 5, right? And then 5 goes to 1. So this is just permutation function with one cycle. Yeah? Okay. I should not really give a dash over here. They have completely different meanings. 2 cycles, 1 cycle. They have completely different meaning. Over here, okay, there is one cycle over here, right? But this thing over here is actually a 5 cycle. I mean, if I give a dash over here, this actually means like how many elements are there in cycle, and this counts number of cycles. So these are different things. Okay, don't be confused about that. And in this video, I'm just gonna refer to this idea of like the way of counting cycles. Like I will not be dealing with the number of elements in cycle in any way. So this is not really right now. But yeah, you should be careful about the way you write it. Let me give a last example. So there's let's say this permutation permutation which takes 1, 2, 3, 4, 5 to like let's say um 3 and then maybe 4 and then I don't know. Look at this. So yes, so 1 goes to 3, maybe over here 1 in here, and then 2 in here, 5 in here. I don't know what's gonna happen, but like it should take 1 to 3, 3 to 4, 4 to 1, right? I don't know. Let's see. Okay. And this goes 1, 2, 3, 4, 5, 2, 3, 4, 2, 1, 5, right? So what's gonna happen over here is okay. So this 1 goes to 3, right? So 3 goes to 2, right? And then 2 goes to 4, 4 goes to 1, and 5 is this. Okay, I need to write this 1 after 4 because that's implied that 1 goes to 3, 3 goes to 2, 2 goes to 4, 4 goes to 1, and then 5 is alone. So this is permutation function with 2 cycles, okay? With 2 cycles, okay. So I guess now you are used to with the idea of cycles, right? And now, okay, how is this Stirling number of first kind related, right? So over here, like you saw some permutation with n equals to 5, k equals to 2, right? And over here, n equals to 5, k equals to 1, n equals to 5, k equals to 2, right? So for now, let me try this. Okay, over here we just saw one of such permutation functions, right? Okay, so for like okay, now let me show you like for n equals to 4 and k equals to 2, how many such permutations functions can be created, right? So let's say from these numbers, let me show you all of them. So one of them can be like 1 goes to 2, and we just want 2 cycles, okay? So 1 goes to 2, 2 goes to 3, and then 4 goes to 4 itself, right? And then notice that like I cannot now write this. This is same thing. Like just like over here, 2 goes to 3, 3 goes to 1, 1 goes to 2. This is same. 2 goes to 3, 3 goes to 1, 1 goes to 2, right? And 4 goes to 4 itself. This is same. I cannot really write this function again, right? Also, I cannot write this function again. 4 and then 1, 2, 3. This is same. 4 goes to 4, 1, 1 goes to 2, 2 goes to 3, 3 goes to 1. So be careful about not repeating the same function again. Now the function could be 1 2 goes to 3, 3 goes to 2, right? And what 2 goes to 1. Next could be something like now 2 3 4 and 1. Next could be 2 4 3 and 1. Next could be 3 1 4 and 2. Next could be 3 4 1 and 2. Next could be 1 2 4 and 3. And next could be 1 4 2 and 3. Okay, so basically there are all these numbers for 1 2 3 4 2 times over here, right? Again, like these are for 2 cycles, right? And there are also other ways to create 2 cycles. I can have something like let's say 1 2 and 3 4. I can have 1 3 and 2 4. I can have 1 4 and 2 3. I can have, maybe you might want to write now 2 3 and 1 4, right? But that's already over here. Maybe you want to write 2 4 and 1 3, but that's already over here. If you want to write 3 4 1 2, but it's already over here, right? So yeah, you don't really need this because those are already over there. So it seems like there are 11 such functions with n equals to 4 and 2 cycles, right? And that gives us the Stirling number of first kind. 4 2 is just 11, right? 8 from here and 3 from here. Maybe you want to also find it combinatorially, right? So for this one, what you can do is, first of all, just choose 3 elements out of 4, right? And then if you fix one of them, rest of them can be permuted. So that's like 2 factorial, right? And then that's just 8. And over here, You can choose two out of 4, but like again, like there will be repetitions. Divide by 2 for this one, so 6 by 2 3, and add these two. So I mean there are, but like you have to make sure that you don't miss any cases, right? So this is how I find Stirling number of first kind. I guess you guys know about that from now. Okay, now let's see how to find recurrent solution for Stirling number of first kind. Okay, so let's say I want to find how many permutation function I can make with n elements in k cycles, right? Now you can get this. Okay, so let's say I have I have n elements, right? Now to get this, like from like okay, so let's just take n minus 1 elements. Let's just know that we know everything about n minus 1 elements. Like I mean, how many like such permutations can be made using n minus 1 elements for any number of cycle. Let's say we know that, and then there is this extra number. Okay, so okay, now notice that uh from like if we have n minus 1 elements, and like let's say we already have we know how many like key cycles can be made from n minus 1 elements, right? So let's say there's this 1, or let's say 2. I mean, like maybe there's this 5 6 of 2 cycles, 3 cycles, I don't know, maybe. Yeah, maybe. Okay, in some ways, like they have already wrote this in terms of k cycles again, and also maybe there's this up to n minus 1, like this, right? So let's say there are already uh k cycles out of these n minus 1 elements. So okay, now in that case, what I can do is this n, right? So this n, like I can just put it after any number, right? After 1, or after 2, or after 5 over here, after 6 over here, or after 7 over here, and that would be like completely new permutation function, right? So while in this ways of n minus 1 elements making k cycles, I still have n minus 1 ways to add in there and make a new permutation, and like that would basically give me like k cycles with n elements, right? So another is like, let's say if I had n minus 1 elements, and like there were just k minus 1 cycles over here, like k minus 1 cycles, right? K minus 1 cycles. In that case, like what to get like this n elements with k cycles, I can just add this last number over here, right, with its own being making its own cycle. So there, okay, so now for this, there's this n minus 1 like k into 1 ways, right? So basically, like from these like ways of n minus 1 elements, like we can get ways for n elements, like uh either like there, if there was already k minus 1 cycle or k cycle, right? If there are, let's say, k minus 2 cycle, that's not even possible. So there are just these two scenarios where which lead to us to these n elements k cycles, right? So from this scenario, I have n minus 1 choices. From this scenario, I just have one choice, and so adding both of them up, we can actually get the recurrence. So this becomes n minus 1, and then n minus 1 k plus n minus 1 k minus 1. I don't know how good I was at explaining this recurrence, but now we have it over here. So guys, try to understand it on your own. If you did good, otherwise let's just take the recurrence and proceed ahead. So now we're gonna use this recurrence to derive this formula, right? So let's see if you can do that. So okay, we are gonna sum all of them from k equals to 0 to n, right? Sum from k equals to 0 to n minus 1, n minus 1 k. Sum from k equals to 0 to n minus 1 k minus 1. Okay. Okay. So now let's say this is our function f of n. So let's say the sum that we are trying to prove, right? We know we are trying to prove that this is actually n factorial, right? So let's just say for now that this function is some function of n, right? Okay. This function becomes f of n, and then this n minus 1 comes out over here. This becomes a sum from k equals to 0 to n n minus 1 k plus sum from k equals to 0 to n again, n minus 1 k minus 1, right? Okay, in the first sum, when k goes from 0 to n, up to n minus 1 it's perfectly fine, right? But when n, we cannot really make a permutation function with n cycles given n minus 1 element. So because that's not even possible, that's just 0. Okay, so the fact that if the number over here, this k, is greater than this number over here, then that's automatically 0. And similarly over here also we get another problem in the second sum. Like when k equals to 0, we have n minus 1 with minus 1 cycles. So that's not even possible. So that's just defined to be 0 again. So yeah, make sure we understand these two things and then we can proceed ahead now. So because those twos are 0, I can actually write this as sum from k equals to 0 to n minus 1 of n minus 1 k, right? And then I can write this as sum from k equals to 1 to n of n minus 1 k minus 1, right? Okay. So now notice that now this sum is going from 0 to n minus 1, and then this is just n minus 1 k, right? So this is just like over here, if we replace n by n minus 1, so you exactly get f of n minus 1, right? So this is also n minus 1 over here, this is also n minus 1 over here. So this should be n minus 1, right? And so you get n minus 1 f of n minus 1, right? But in this next scenario, now you can try to shift the sum. What we try to do is we can just say that, let's say if k minus, okay, over there this sum goes from k equals to 1 to n, right? So I can say that this sum goes from k minus 1 is equals to 0, right? Okay, and then now this goes from k equals to 1 to k equals to n, right? So what I can actually try to do is, if I just let it go from 0 to n minus 1, and then I can just add 1 with the k minus 1 over here. That perfectly makes sense, right? Basically, even now, even earlier, it was this k minus 1 would have gone from like 0 to n minus 1, right? So that's what I'm doing. I'm just trying to rewrite those variables. Okay, now again, we see that this is again the same function with all this n replaced by n minus 1. So that's also gonna be f of n minus 1, right? So now if you take f of n minus 1 common, you see that f of n is equals to n times f of n minus 1, right? Okay, now let us try to find f of 0 from this sum. F of 0 is just going to be sum from k equals to 0 to 0 of n k, right? Okay, n is 0, so 0 k, right? Okay, now definitely there's no, like, we cannot make really one cycle or two cycle from 0 element, but you can make 0 cycle, right? That's just one way. So we just define that to be 1 because like from 0 elements 0 cycle like one way, right? That's the definition, and that becomes 1. So from there, since f of 0 is 1 now, we can find f of 1 using 1 times f of 0, which is just 1, right? And the f of 2 is like 2 times f of 1, and f of 1 is 1, so 2 times 1, right? F of 3 is 3 times f of 2. F of 2 is 3 times 2 times 1. So this is like 3 factorial now, right? And f of 4 is 4 times f of 3. F of 3 is 3 factorial, so 4 times 3 factorial, which is 4 factorial, right? And then you can actually now prove by induction that f of n will just be n factorial. That is it, guys, and that proves. You can I leave the proof by induction on your own because that's really easy, and that proves the thing, right? So once you have induction, it wasn't really hard, but like I was also trying to give a 1-1 intro class to Stirling Number of first kind, so that took time. Yeah, okay. So to recap, we first talked about the permutation function and the cycle notation, and then how to find the Stirling number of first kind, and then how to make sense of recursive relation from that, and then how to use recursive relation to find the function, and there's some definitions over here, and after that we found that function should be n factorial. That means this thing over here, this sum over here should just be n factorial, right? And so that's what we were trying to prove. So that proves it, guys. So that proves that this function over here is this n factorial, and that concludes our video. I hope you guys understood the video. Thanks for watching. And now I think definitely I'm gonna come with a lot more videos on Stirling number of first kind and second kind. Though officially I didn't really make any intro videos for both of these, but like I definitely explain both of these in the first video of second kind and now in this first video of first kind in my channel. If you are following, definitely you get an organized video sequence. Otherwise, maybe no, I don't know. But yeah, I hope it's helpful. Thanks for watching, and I look forward to seeing you in the upcoming videos too.